maybe we should go to the specific questions for the modelers. And I'm having some sort of problem with this. It's cutting off at the top. All right, so just to motivate the discussion, the ground motion simulations from the broadband platform are going to be used to inform for cases lacking empirical constraints, as Jennifer and Katie both pointed out earlier this morning. And what that means for the Diablo Canyon Nuclear Power Plant is using the simulations to generate ground motions for moderate to large events located within 20 kilometers of the site, and inform on the nature of the ground motions for shallow dip angle cases where there is not much in the way of empirical constraint. And as Jennifer has been looking at evaluation of the hanging wall effects on the ground motions. So using this new set of simulations to help inform on that. And then, as Katie pointed out, using the ground motions from large multi-segment and splay faulting scenarios. So just to motivate, okay, so we've used the broadband platform to generate ground motions from 3 methods, ranging in magnitude from 5.5 to 7.5. And throughout the process, the TI team has coordinated efforts with the broadband platform and the modelers during weekly conference calls. Make sure we're on the same page. Discuss questions with respect to interface and preliminary results and those sorts of things. And then on September 26th, we had an in-depth review and analysis and discussion at USC with the modelers. And at that meeting, we found some really interesting observations. We made some interesting observations. So these are the questions. I'm going to skip over that because they're on the screen. And just to partly motivate some of these questions is, for example, these are plots that Katie prepared that if we look at the upper right panel, it's looking at the residual between the GNP method and XSIM. And this is for a magnitude 6.5 case with a Z-Tor, top of the fault at 0 kilometers, dip of 45. And what we're finding, and so here we have the surface projection, or the surface of the fault, and it's dipping to the right here. And so there's this distribution of stations, and what's being plotted is the residual between those 2 methods. And so there's a comparison between GNP and XSIM, and San Diego State and XSIM, and San Diego State and GNP. In this particular case, is for PGA, so it's high frequency. And so what one sees is that there are differences at the surface projection of the dipping fault plane. For example, just focusing on this, you can see that that the bias is tending towards negative values. And what's interesting is that it's going toward the footwall side. Okay, so it's extending beyond the surface projection of the dipping fault. So that's an interesting observation. And then if we look at the comparison of the 2 hybrid approaches, you can see that there's quite a bit of variability, which is probably due to differences in the stochastic components of those models at those short periods. Because if you go to 3 seconds period now, you can see that the 2 methods, SDSU and GNP, are essentially the same. Okay, so we don't really see any difference with respect to hanging wall and footwall from these 2 methods. And we're at the deterministic part of the ground motion simulation. But if you look at, again, differences between GNP and XSIM, you can see that there's fairly large differences. And that extend also onto the footwall, and that's true for SDSU. And there's also some interesting patterns extending in the footwall away from the surface projection of the fault, which suggests some radiation pattern effect. That's common to SDSU and GNP, but not XSIM. Okay, so another series of plots that we're going to see more of later this afternoon, I think, is looking at perpendicular profiles over a buried fault. This is a case with a Z-Tor at 7 kilometers. It's dipping 10 kilometers. These greenish symbols are the XSIM results, and GNP and SDSU are shown by these values. They track very closely. This is for 3 seconds period. And one of the interesting observations is that there's a relatively wide plateau that appears to be a hanging wall term, but that there's structure in it. In particular is what Jennifer's referred to as a divot. Okay, so it becomes a large amplitude and then it divots down, relatively large plateau. So at our discussion on September, we feel like we understand these, but these are some really interesting observations that we have not seen before and warrants additional discussion. So that's for a dip of 10 degrees. You go to 30 degrees. The important point here is that you see many of the same sorts of features, but the location of the divot and where the peak amplitude occurs changes. It's clearly a function of fault dip. And this is, again, a magnitude 6 case for a 30 degrees. So again, it changes. So if I just go through those quickly, you can see a fairly large function of dip. And well, it's clearly something that's different from these two models and the fully stochastic approach. Likely some superposition of the radiation pattern, we think. So it's an interesting observation. And if you look at one particular method and then look at models that have the same dip but different z-tors, depths at the top of the fault, then you also see some systematics there too. So for z-tor, the shallowest, you have really a single peak that's coming up, and then as you go to 7 and 12 kilometers, this dip and where the peak on the footwall occurs moves out away from the surface projection of the dipping fault. So these are some very interesting features that have not been observed before, and we need to understand them to motivate the discussion. Skip that one. This is a comparison for XSIM now. Again, for the same dip, 10 degrees, z-tor of 2.57 and 12, same plot as before. And what you see is something that's a lot more systematic in terms of what could be described as a hanging wall effect. And so the question is, what is the controlling parameter here and what's different? And we don't have to discuss all of these right now because we'll have a discussion now more generally based on these questions. And the modelers have prepared some short presentations to address these particular questions. But after the break, Jennifer will be presenting some of this and we'll have another discussion. And then on day 3, Katie will be presenting the more complex and splay rupture cases. This motivates that last case, day 3 discussion. And so this is looking at what are referred to as GNP simulation thin model, SDSU thin model, XSIM thin model. Okay, so these are GMPs, function of frequency, spectral acceleration. And one thing you can see is that the two hybrid approaches are very similar at low frequencies. They should be. But there's relatively large differences at high frequencies, which is due to the manner in which the stochastic element is produced. And then this is showing the comparison between the GMPs, some of the GMPs, and the simulation results. So again, these are differences that we'd like to explore a little bit more carefully and get a deeper understanding of. And so that motivates the questions. And so the first general question is, based on the September 26th SCEC meeting, is the output of the broadband platform consistent with expectations for the method? Is there anything in the simulations that stand out as problematic? Another general question addresses application of the approaches to very large magnitudes approximately 8. Can the model be applied to both surface and buried ruptures? Are there any things to worry about there? Any limits on how close to the fault the ground motion simulations may be used? So I think what we should do now, in the interest of time, is switch to a modeler presentation.